All right, we are live, and yeah, just gonna continue from the previous streams for I don't know, reading some recommender system papers. Today I had wanted to take a look at. Let me see this one. So the previous one we looked at Netflix, but was sort of their paper from 2015. This one is from 2021, where they have made sort of a Netflix case study, and they talk about sort of traditional algorithms for recommender system versus deep learning approaches. So I want to take a look at that, and then also this. I've taken a look at this one in the past, but I haven't gone into it in sort of detail, and I think I should because this is a really influential paper in sort of introducing deep learning to recommender systems. So yeah, we'll do that. We'll do the other paper, and then we'll see. Maybe we can do some, depending on how much energy we have, maybe we'll do some implementation of, I don't know, yeah, we can take a look at some data set and try to implement stuff. So let me check if it is actually live. Okay, I don't know. There's always some type of like the chat not working. I don't know. Like sometimes it takes time or something for it to pop up. I'm not sure. Uh, but yeah, I'll have the comments here after a while. So if you have any, like if you, I don't know, got any questions or anything, then let me know, I guess. Yo, there we go. All right, I'll just use this one on the other screen. Cool, cool. All right. Yeah, let's just start to go through it. So I don't know. I just found this one and I thought it would be interesting. Pretty good follow up on the previous one. So let's see. Deep learning for recommender systems, a Netflix case study. Uh, deep learning has profoundly impacted many areas of machine learning. However, it took a while for its impact to be felt in the field of recommender systems. So that was probably like 2017 for deep learning, like with the NCF paper, this one. So I guess it took a while. Yeah, like there's definitely some delay there. In this article, we outline some of the challenges encountered and lessons learned in using deep learning for recommender systems. We first provide an overview of the various recommendation tasks on the Netflix service. We found that different model architectures excel at different tasks. So this is like one thing that that I basically the last video or live stream, we looked at this Netflix paper that showed, how they have like millions of recommender systems for everything. So you have one recommender system for like popular ones, you have one for like because you watched, you have one for search, you have one for the rows, you have one for like everything you can imagine. It's a specific recommender system. And I guess it makes sense. Like if you think about it, like the revenue that they generate, if they increase by 2% because they use a specific one for this specific row, that's you know, yeah, whatever. I don't know what the rows are for Netflix, but yeah, imagine like 2% improvement in the revenue. It makes sense to have, I don't know, 30 people working on that recommender system. But on the other hand, at the same time, it feels super over engineered, right? It's like, what are you trying to accomplish here? You're trying to accomplish creating a recommender system that gives you great movies. Is it really necessary to have, I don't know, 50 people working on for one specific row on that specific recommender system? Because increasing that for like 2% gives you, I don't know how many millions in extra in revenue. So like, it makes sense that they would want to have many different model architectures because they excel, at that niche thing. But on the other hand, it feels over engineered. But I don't know, you can't argue with revenue. So, I, just as a gut feeling, it would feel really good if you would have just one system that's polished and just does everything. But yeah, it's just not that. Yeah, I can send the paper link for this one. Let me see. Yeah, there's a bit of a delay on this one. I'll fix it for the next time. I put like normal delay, but it's a bit too long delay for the chat. But if you have any questions or anything, let me know, and I'll just pause and just we can chat a bit too. All right, so let's continue then. Okay. Even though many deep learning models can be understood as extensions of existing simple recommendation algorithms, we initially did not observe significant improvements in performance over well-tuned non-deep learning approaches. Only when we added numerous features of heterogeneous types to the input data, deep learning did start to shine in our setting. So I guess that's, one big pro of deep learning, right? You can sort of put in whatever you want, and it will just figure out. If you do matrix factorization, it's very difficult to put in all types of signal. Where do you put in the time with where they watch the movie, for example? Or what device did they use when they opened it? Were they using the phone, or were they using the like the TV? Maybe that influences what types of recommendations do you want to make, and that's very difficult to put into a matrix factorization solution. All right, we also observed that deep learning methods can exacerbate the problem of offline-online metric misalignment. Curious about that. I'm not familiar with what that misalignment is. After addressing these challenges, deep learning has ultimately resulted in large improvement to our recommendation as measured by offline and online metrics. On the practical side, integrating deep learning toolboxes in our system has made it faster and easier to implement and experiment with both deep learning and non-deep learning approaches for various recommendation tasks. We conclude this article by summarizing our takeaways that may generalize to other applications beyond Netflix. All right, so it seems like they have been able to improve substantially with deep learning. So my feeling has been that in industry, people really like simpler recommender systems, maybe even rule-based, heuristics-based. But when you read a lot of papers, they seem to really push towards deep learning. That, if you look at YouTube recommender system, this one, Netflix recommender system, and the Google ads, all of these, they use neural networks, but that might be what you see in papers, and then what you see in practice, if you go to these companies, maybe it's very different. Is my feeling, at least. So that is something to keep in mind. Okay. In the early 2010s, deep learning was taking off. By the way, let's just do as we normally do, like reading papers. It's very rarely, I usually spend a lot of time on the abstract, like to get a sense, because it does give a good overview. but then I don't want to spend that much time on reading everything here. So we'll just take a look, first. Uh, uh, like introduction, deep learning was taking off, something NLP, deep learning is useful, recommender system, the path has been maybe not so clear. All right, recommendations at Netflix. Basically, they talk about various recommendation tasks. Okay, so this is interesting. Modeling approaches. This is what I'm curious to read about. Bag of item approaches. Let's see. They also have a figure here. So simplified relationship among several models, matrix factorization, asymmetric matrix factorization, transformer, RNN. Okay. Feed forward autoencoder. Okay. I'm curious about that. Sequential models. While the bag of item is convenient, there is a sequential nature that gets removed. That's very interesting. Like I saw that too. Like there was a paper, sequential transformers or something, where they included the time, and that has useful information. Adding heterogeneous features. Yeah, so this is the strength of, I would say, deep learning approaches. They can use these. Ranking improvement, baseline plus discrete plus continuous time context. That's a lot of improvement over the baseline. All right, practical challenges, mismatch in offline and offline, online and offline metrics. I'm really curious about that. Aspects of the industrial setting, and that's it. All right, so there's a lot of details we missed, right? But just getting an overview, and then we can go through what we want to learn about. All right, in early 2000, deep learning was taking off in the machine learning community, fueled by impressive results on a variety of tasks in different domains, including computer vision, speech recognition, NLP. At that time, there was a stir in the air within the recommender system research community. Will the wave of deep learning also wash over recommenders to deliver tremendous improvements? As with many others, we at Netflix were intrigued by this question and the potential of deep learning to improve our recommendations. While the answer is now quite clear that deep learning is useful, the path to understand where deep learning is beneficial over existing recommendation approaches was an arduous one. This is evidenced by how many years it took for such method to get traction in the research community. But it was a rewarding path, as evidenced by a subsequent bloom of work on the subject. Our own investigations into deep learning at Netflix took a similar path. Initial exuberance faced the stark reality of well-tuned baselines. So this is my feeling from working with recommender systems now in actual application based, where you get this feeling that people are really I don't know why. If the baseline works so well, then it might not make sense to spend that amount of time of like the additional technical depth you get from deep learning based. So yeah, this is if you introduce a deep learning based approach, I think you have to be expecting some pushback, because it is more technical depth, just more complicated than a simple. But on the other end, if you do what does a well-tuned baseline mean? Is this like a rule-based heuristic, or is this SVD approach? Is this I don't know what this means exactly. This led to a clear understanding of the relationship between deep learning and other recommender models. The obstacles gave away when we combined the lessons from these approaches with insights about what kinds of problems different deep learning approaches excel as well as their limitations. Along the way, it also yielded practical lessons on how to get deep learning to work in real-world recommendation settings. In this article, we first set the scene for our journey with an overview of various personalization tasks at Netflix service and a focus on the key task of personalized ranking of movies. We then discuss several specific properties of the data available in recommendation settings like at Netflix and the practical challenges they impose for creating recommendation algorithms. All right, looking at deep learning through a recommendation lens. All right, let's just skim this a little bit. First, we discuss bag of items. They ignore temporal information. After initial struggles, they especially start to shine when we provided with additional heterogeneous features. In contrast, other models remain competitive when we only use user item interaction data. However, this flexibility of deep learning models allows us to find scenarios where we could build However, this flexibility of deep learning allows us to find scenarios where we could build models that obtain large improvements in offline metrics evaluated on historical data. After finding improvements in offline metrics, we subsequently found that these gains, even when very large, did not always translate to online performance in A/B tests with real members. To address this, we needed new offline metrics that were better proxies of the online metrics. And far from that, we cover additional practical aspects required to use deep learning in our recommendation system, supporting hundreds of millions of members. Okay. So basically, like they used, like you can, the neural networks have high flexibility. You can easily add new features to, like inputs to them, which is difficult on other traditional algorithms. So that's like the biggest thing, but they seem to overfit or like perform really well on offline metrics, but that it doesn't translate. So that is basically the gist here. Finally, we focus on the key learnings. We will also outline takeaways that may generalize to other applications as well. Yeah, a bit weird. The main task of our recommendations by Netflix is to help our members discover content that they will watch. Yeah, blah, blah, blah. Yeah. At Netflix, there is no single model that drives all recommendations, but rather a set of techniques that are all aligned on their goal to increase member satisfaction. Through experimentation with various kinds of recommendation algorithms, we found that there's no silver bullet. Okay. Okay. At Netflix, there is no single model that drives all recommendations, but rather a set of techniques that are all aligned on their goal to increase member satisfaction. Let's see. Different kinds of machine learning models are used to generate personalized recommendations. Various aspects of the Netflix recommender system prior to using deep learning. Okay, dividing the recommendation problem in multiple subtasks allows us to combine a diversity of different approaches and also make the research and development of new or improved recommendations more modular and scalable. So basically, here's the highlight of the, like, they have various recommendation tasks. I guess one, I'm not sure what the one is. For example, there's a dedicated algorithm for choosing the first video to display. Okay, so here's like a video, I guess. So this is one recommendation algorithm. There's one for search. There's one for notifications. There's one for the rows, I guess. There's an algorithm that selects which rows. And then where's 5? Discover new video. I guess so. There's like one to give you which rows. There's one to give you which in that row, for every row. Yeah, there's just a lot of different different ones. Let's skim this a little bit. I don't think this is too interesting, maybe. Let's see. So here they just talk about the figure. Besides the recommendation task, the available data and its properties have a crucial impact on which algorithm works well. The first and most important distinction is whether the data contain only the user item interactions, as is often the case in publicly available data sets, or additional information like user attributes, item attributes, or contextual information regarding the user item interaction. Through experimentation, we found that more complex models, including deep learning, shine when we enrich data with such additional heterogeneous features. Even though several common properties of the data have been discussed in the literature of recommender system, it is worth reviewing them briefly before we outline additional challenges. The key differences to the data sets used in other domains are as follows. First and foremost, the observed collected data are missing not at random. That is, entries with observed positives, played videos, clicked items, given ratings are not randomly distributed in the user item interaction matrix. There's a crucial difference to fields like compressive sensing or matrix completion, where the entries in the matrix are typically assumed to be missing at random. Second, the unobserved entries in a user item interaction matrix may either be true negatives, i.e. the user is truly not interested, or positive that were not observed yet. Third, the observed data are typically extremely sparse. All right, so I'm not sure exactly what they're sort of the point that they tried to. I mean, this makes sense. Like, you want to use them when you have additional features. Okay, so like a problem is that the observed collected are missing at random. That's not like true, I guess, in practice. Second, the unobserved entries in a user may either be true negatives or positives. Third, the observed data are typically extremely sparse, and the observed positives are very noisy as they originate from a stochastic process. Fourth, there is a large popularity skew present in the data that it is the popularities of the various items follow approximately a power law distribution. Okay, just like this, you have some popular items, some movies are watched a lot more, resulting in many orders of magnitude in differences in the popularities of the various items. Regarding the users, there is a similar approximate power law distribution with a small number of very active users and a large number of less active users. This power law distribution can cause modeling challenges due to distribution mismatch. It also poses a challenge in making fair and accurate recommendations. Okay. In a real-world recommender system, the various biases in the user item interaction data, like presentation or position biases, can possibly be amplified due to a feedback loop. Okay, so this is interesting. So in the real world, the various biases, so you have, presentation bias where if you give them the first item in the row is more likely to be clicked just because it is the first item. It's just shown, displayed, to the user. And they can be amplified due to a feedback loop where the recommender system is trained on the observed user from a previous time step. So like, I guess if you show them the first item, then that might be clicked a lot more because of the fact that it was recommended, and then that will get even stronger signal to the recommender system that this should be displayed because it is watched a lot, but it was only watched because it was recommended. So this is like a difficult challenge. This is due to presentation bias, where users are more likely to interact with items shown more prominently by the system. Breaking or at least dampening the feedback loop is a key challenge in a real-world recommender system. This poses not only a challenge for training recommender systems on the data that have been collected, but also result in a notable mismatch between offline and online metrics. So just like these biases are extremely difficult, and they cause a lot of, you need to be really careful of how you train them, the offline metrics you use, because there are all these biases. Basically, like, recommender systems are really hard, I would say. The dead internet theory, I'm not familiar with that. Is it like you would have chatbots or something that would be basically GPT taking over, or what does a dead internet theory mean? Modeling approaches. In this section, we outline our learnings when experimentation with various deep learning models for recommendations from simple baselines to more complex approaches. We divide these models into two groups, bag of item approaches and sequential models. Properties that are common to both types of models are discussed as well. Following that, we describe our key insight, namely that deep learning algorithms for recommendation excel at combining many heterogeneous features. In contrast, we found that simpler models that are well-tuned were competitive when only the user item interactions were used. Bag of item approaches, how do you even pronounce that? This word. Bag of words approaches in NLP. Many recommender systems make the bag of items assumption, bag of videos in this case. In this approach, the model ignores the temporal order in which a user played videos and instead treats them as a set. The most common way to represent the training data is to turn the data into a sparse user by item matrix, where each non-empty entry represents the user feedback on an item. Okay, compared to words, the amount of sequential information in video engagement is lower, with some exceptions like movie sequels or episodes of TV shows. Though there are also some temporal dynamics due to viewing trends, the bag of videos assumption can provide a useful approximation to the real world when we model a user's long-term interests, which tend to be relatively stable. Yeah. Yeah, it's not impossible that, I think it will probably be, if it's not already, it will probably become very bot dominant, I guess. Yeah. I don't know. It would be interesting to know if somebody would collect like the statistics of, it's gonna increase, right? But it's gonna plateau at some point. Uh, I'm curious about that as well, like how the internet is going to change because of that. I think, you're gonna have people are gonna have to have identity on on like on Twitter, for example. They want to introduce this, Twitter Blue, because basically, I guess make money, but also to circumvent the bot problem. And that seems like, in general, people are gonna have to show to be have an identity online. I think it's gonna be difficult to be completely anonymous in the future and to be taken seriously, because there's a high likeliness of you being a bot. I might be a bot. I don't know. I should just like train a neural network to imitate my voice and the video with some, I don't know, stable diffusion process or something, and then just turn it into a video. That way I can just ask GPT to write scripts for tutorials and record them, and then I'll basically have, I don't know, a million videos uploaded every week. All right, where were we? Um, let's see. The bag of videos assumption. Do, 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 do. Because of this and the sparsity of feedback, we have found it important to understand these long-term interests in our recommendations. In the literature, especially the Netflix prize competition, several bag of items were developed, restricted Boltzmann machines, as well as variants of matrix factorization models, such as SVD++. This is the paper we read, SVD++, or asymmetric matrix factorization. This I have not taken a look at. I only read the SVD++ one. Interestingly, both techniques have connections with deep learning. Around the same time as the Netflix prize, restricted Boltzmann machines were also used to pre-train. Okay, this is getting out of hand. Okay. Autoencoders have been used in various applications, including machine translation, computer vision, as well as recommender systems. Okay, an autoencoder is comprised of two parts, an encoder and a decoder, both of which may consist of several hidden layers with nonlinear activation functions. The encoder converts the input vector. All right. The autoencoder subsumes several traditional recommender systems as special cases. First, asymmetric matrix factorization can be viewed as a linear autoencoder with a single hidden layer. Note that asymmetric matrix factorization is different from standard matrix factorization in the following way. When training data are given in the form of a user video interaction, matrix factorization learns a matrix of user embedding as well as matrix of video embeddings. All right, what? Asymmetric matrix factorization. I'm not too familiar with, like, what do they mean? Let us um, So let's see, they talk about asymmetric matrix factorization and I don't know, and SVD. So wait, SVD is a matrix that decomposes into three. It assumes that the input matrix is symmetric. Why does it, let's see, so the transpose is equal to y. I don't know, I'm confused. I guess this is like it assumes maybe some type of asymmetric refers to the fact that the user item matrix is not symmetric, meaning that the interaction from user to item is not necessarily the same as from item to user. In traditional matrix factorization, we decompose the user item interaction into the product of two lower. However, in asymmetric matrix factorization, we take into account the fact that the influence of an item on a user rating is not necessarily the same as the influence of a user on an item's rating. This is particularly relevant for implicit feedback data sets where we only observe positive interactions. All right, and the absence of an interaction does not necessarily mean a negative preference. For example, consider a movie recommendation. If a user watches a movie, that's a clear signal that the user is interested in the movie. But if a user doesn't watch a movie, it's not clear what that means. It could be the case that the user is not interested, or it could be the user hasn't discovered the movie yet. This is an example of the asymmetry. In asymmetric matrix, we might model this by having separate factors for the user's influence based on the movies they've watched, and the int item influences on the user based on the users who've watched the movie. Okay. All right. Might still have some lack of understanding there, but um, in contrast, asymmetric matrix factorization learns two different matrices of video embeddings and constrains the user embedding to be the average. All right, let's just be okay with not understanding this completely right now. In standard matrix factorization, making recommendations for a new user or updating for a user with new data would involve an optimization procedure. Okay, fold in to obtain the corresponding user embedding. This typically involves running one step of an optimization algorithm to solve for the user-specific parameters while keeping the item embeddings fixed. On the other hand, this folding procedure is not needed by using asymmetric matrix factorization, or more generally, nonlinear autoencoder models, where recommendations can be computed by passing the input vector through an encoder and decoder. This amortized inference provides widely applicable across many domains. Second, neighborhood-based approaches may also be understood as a special case of autoencoders. So basically they're saying that, asymmetric matrix factorization, autoencoders is the general case of that, you could say, and then that neighborhood-based approaches could be seen as a special case of autoencoders as well, given that both approaches are based on an item-to-item function. If we increase the dimension of the hidden layer in a linear autoencoder to be identical to the number of items in the input, we obtain a full rank model instead of a low rank model as typically used for autoencoders. That is equivalent to a full rank model having a single item to item matrix of model parameters. This matrix corresponds to the item to item similarity metrics used in neighborhood based models. Okay, so they're basically trying to a simplified relationship among several models. So you have matrix factorization. What does the arrow mean here? So the arrow, this is more general, right? So asymmetric is a part of matrix factorization. Autoencoder Yeah, thanks for joining, Clayton. All right, so they're basically saying that this is a special case of this, which is a special case of this or this. And autoencoder is just. I am a bit confused over this figure here, but basically you have, I don't know, because I think what they talked about here, right, in this paper here, is that they said that the this was a special case of this. Maybe I misunderstood that. Okay, first, asymmetric matrix factorization can be viewed as a linear. Okay, yeah, so this, I'm thinking, if you say that this can be viewed as this, then that they're a special case, but this is yeah, I'm not sure actually. This is a bit confusing here. I wonder if this works. Yeah. Yeah. Just this that comparison is a little bit difficult to understand there. Deep forward model may be viewed as a generalization of the autoencoder. So basically, they're saying this is a generalization of this. So this is a generalization of this. Major fraction is a generalization of this. And this is a generalization of, or this is a generalization of this. Okay, I don't know. I don't know. I just feel like they made this super complicated with this seeing things as generalization of other, like it's just confusing to me actually. Uh I don't know if I share this into it. It's not, I don't, maybe it makes sense. I'm not sure. All right, basically what they want to say here is that, hey, through the lens of autoencoders, actually several unrelated models are in fact closely connected. This can help us better design recommender system for specific needs by flexibly combining different models. It also provides insights on how to further improve different models. Cool. All right. While the bag of items view is convenient, there is useful information in the sequential nature. Many of the deep sequential models can be adapted. Instead of predicting the next word, the recommendation aims to predict the next item that the user will interact with. Sequential methods are very effective in e-commerce for session-based recommendations. The lack of clear user identifier means that the only known information in the sequence of item visited so far within the user session. Several models were found to show good performance. Basically, they've explored with this, and yeah, it basically improves. All right, so adding heterogeneous features, this is like the big strength. I feel like they're saying where you can send in a lot of extra information. Okay, so after we struggled to obtain significant improvements, we, in comparison to well-tuned simpler, we took a step back to think about what deep learning could potentially enable us to do and what was difficult with traditional models. We hypothesized that deep learning and deep models could be particularly effective in making use of extra information beyond the user's implicit or explicit feedback. Indeed, when we carefully added additional information, we obtained large gains in recommendation accuracy. I'm also curious, like, okay, so if we, it's obvious that we can just give that information, like, here you go, this is the device they use, this is the time of day that they watched it, or open Netflix, this is, whatever, and you can get all this extra. But how do you then maybe remove some that aren't, like, if you train on that and then you realize that, hey, maybe the device that they, I don't know, some specific feature is not important, then, oh, it's raining a lot. Yeah, so anyways, basically, how do you then check, to check which features you can, which were important or not? I guess there are methods for that separately, but yeah, I'm not too familiar with those. I guess you could do some type of checking of the weighting of the neural network to different types of features. In the following, we use the example of leveraging time as an additional feature to illustrate the power of deep learning and representation learning. First, note that the time is not easy to represent within linear models. Yeah. So, there's a lot of different things that are difficult to put into traditional models. In recommender system, it has been shown that incorporating time increases model performance. All right. Yeah, so we use continuous timestamps indicating when the user played a video, when the current time. Yeah, so basically when they add discrete context, they get this, but when they add continuous time context, they improve a lot, and slightly better if they use both. Continuous time features. So wonder exactly how that looks like. Like indicating the time when the user played a video along with the current time. So why would using the time give that much more information? And why is it such a big improvement over discrete time context? So I guess, like if you give the time, maybe they're more interested in watching specific types of movies in the morning versus the afternoon, right? Like you just wake up, you want to, I don't know, make sense that would have an impact, right, in the day, but that it would be this big. I wonder how they discretized the time context here. Hi, Riyad, welcome to the stream. All right, so anyways, let's see. Linux, which this is Mac. All right, so first, there is no need to define an arbitrary discretization schema, which can be challenging when dealing with behaviors from people in various time zones around the world, as well as with different interaction frequencies. Second, a simple representation of the data allows the model to learn and extrapolate trends. However, as usual with deep learning, explainability becomes more challenging. Moreover, when using raw timestamps, the production algorithm would always use the current timestamp, which was never observed in the training set. Okay, it is an open question how far ahead in time these methods can extrapolate and how fast the performance of the production system degrades without being retrained. For this reason, we ensure that such models are regularly retrained to prevent the need to extrapolate very far beyond the training set. Apart from incorporating additional context or metadata features, personalization can benefit from using computer vision and other content understanding techniques. Yeah, so you can add in all these additional stuff, right? So like you can add features of the image or audio or whatever directly to your recommender system, which is very difficult to do otherwise. Okay. Yeah, so they found it difficult to incorporate those complex features. Yeah. So in contrast, deep knowledge, I'm able to learn the relevant in an end-to-end fashion to produce considerable gains in recommendation accuracy. All right, so now we have practical challenges. Using deep learning in industry brings forward many challenges and learnings that makes it different from an academic setting. You have mismatch in offline and online settings. A common problem when developing a recommender system is that offline performance is not reflective of online performance. We observed this acutely when trying deep learning models. In some cases, we saw significant when tested online. They would disappear in rare cases, resulting worse. This is generally a manifestation of correlational performance not being indicative of causal behavior. But why would this problem be exacerbated in the case of these deep learning models? We would like to highlight a few observations. All right, so you have sensitivity to objective functions and proxy metrics. So you have some short-term proxy, clicks or plays, but what we want to maximize is long-term user satisfaction. The connection between these proxy metrics and the actual may be quite complicated and may even break in certain ranges. Therefore, if a machine learning model overfits to these short-term metrics, it may possibly deviate away from the actual metric of interest. What do you like more, classical machine learning or neural network? Because for me, I'm getting kind of bored of tweaking my model and doing feature engineering stuff, and I want to get into deep learning. What's classical ML to you? And because I think like you'll be doing the same thing, no? Like tweaking the neural network and doing feature engineering. All right, so all right, simply speaking, if a deep learning model is giving the wrong problem to solve, it will solve it more accurately than less powerful models would. So that's yeah. We need ways of training. We hence need ways of training to optimize long-term behavior. An additional challenge is that short-term actions can be quite noisy in the sense that subtle changes in the definition of the short-term training objective can lead to big changes in the produced recommendation. Distribution mismatch. This is in general true whenever machine learning models are deployed in the real world. That is, the data which are used to train machine learning models are not reflective of the population for which the model will be used. Covariate shift is a concrete example of distribution mismatch in which the distribution of input features is different. Covariate shift, what's that again? Covariate shift. So like you have a distribution shift from what exactly? Yeah, so like, yeah, I guess you would, it would slowly change, right? You would need to constantly update your recommender system or the model parameters because the training and the real world data shifts. Traditional techniques to fix distribution mismatch, like importance sampling, has been shown to be less effective with powerful deep learning models. These problems are well known. Fairness and explainability. Wow, yeah, the delay is quite large on the stream. Right, I meant by classical like basic statistical algorithms like linear logistic regression. I mean, yeah, like I unfortunately think that you will encounter the same type of boring problems with deep learning. It's not like it's going to solve those things. You're still going to be tweaking the model, probably going to be tweaking the model more because there's more hyperparameters, and you're probably gonna have to do a similar amount of feature engineering, and you're probably gonna have a lot more headaches when training. I think fundamentally it depends on the problem that you're working on. If you can solve the problem well by using linear regression or logistic regression, then there's no need to use deep learning. It's a tool that you can utilize that shouldn't be overutilized if you don't need it. But if you do need it, or it will improve performance a lot, then I do think it's worth to spend the time of using it. All right, so another is fairness and explainability. All right, cool. Deep learning models are complex and hard to explain. We found techniques like LIME and SHAP and integrated gradient to be particularly helpful in explaining deep learning models. Okay. Let's just skip this. Okay, here we go. Wait. All right, so they use contextual bandit techniques, are in particular able to break the feedback and remove various biases in the data by introducing some amount of randomness in the recommendations. With bandit algorithms, we can continuously gather cleaner training data by keeping track of the propensities for the shown recommendations. Even though the user experience may be occasionally slightly degraded in the short term, it helps improve the quality in the long term. Okay. A complementary approach to exploration is to use the fact that there are different ways of discovering videos on the Netflix service. Okay. Let's see. So basically, what did they try to do here? The problem was overcoming all meant iterating, tweaking, and refining. In the process, we not only improved our models, but also our metrics. Off-policy evaluation and the use of bandits. Okay. A complementary approach to exploration is to use the fact that there are different ways of discovering them. Of course, this approach is only applicable in recommendation tasks where there are several ways. All right, let's skip that. Aspects of the industrial setting at a scale of hundreds of millions of users. Machine learning models analogous to a kernel in an operating system in the sense that a lot of work is put into developing the surrounding ecosystem. so that the model works well. Therefore, it is important to consider practical aspects. Deep learning software and hardware infrastructure. Neural networks have been winning the hardware and software lottery. This means that in recent years, we have seen plenty of advances in industrial strength machine learning development and the deployment ecosystem. Is machine learning or data science a statistical field for me or a computer science one? Like I would say, like I did when studying courses, I took CS 229 um, online from Stanford. I think they really emphasized the statistical aspect, and they showed how to derive a lot of different of these algorithms from you know like maximum likelihood and so on. And I think those make sense and that they are valuable, that statistical aspect. But to be honest, from just getting things to work and just putting things in production and iterating on these algorithms, I definitely find that it's more computer science than mathematical or statistical. I think the mathematical and statistics is important in many cases to understand how they got things to work in many cases, or like how they approach the problem. And yeah, like it can be interesting for that understanding, but to get things to work, it feels like it's mostly computer science. So yeah, like my undergraduate is in mathematics, but more and more I lose. It's very rarely that I use that mathematical part nowadays. Even when reading papers, it's more general ideas and things like that. To understand these approaches, they're more intuition based than like well developed in statistics, I would say, for most cases. Not always true. So I would say, yeah, like it's mostly computer science. All right, let's skip this. I don't know how important this is. I don't know if this paper was that good, to be honest. I don't know how good this paper was. Like, I don't feel like. Okay. Conclusions: making deep learning models successful and widely adopted within the Netflix recommender system. Okay. Sometimes only has limited benefit. Um, yeah, I don't know. Like, all right. So, like, takeaways from this paper. Oh my God. Like, the takeaway is that deep learning works well when you add more features, and that if you don't, if you only rely on user item interaction, then matrix factorization is good, very good baseline. And I don't know, that they use contextual bandits sometimes, and that continuous time context is important. I don't know. I don't know, man. This paper was how many? I don't know. Wonder if like where did I get this paper from? Okay, it has 50 citations. So I guess it is pretty good. I guess I don't know.
Hello, I'm Harold. This is member satisfaction, the two specific recommendation tasks, more things. For this reason, we use many different recommender systems at Netflix, which are tailored to the specific recommendation tasks. To this end, we found it helpful to understand how the various kinds of models are related to each other, which we discuss in detail in the article, including the neighborhood-based approaches, the classic matrix factorization models, as well as the deep learning models. In this article, we also outline our main insights when deploying deep learning models as recommenders learning approaches. Learning models, as they exacerbate biases in the training.
All right. Yeah, okay. I mean, it was. I don't know if I got too much insight, I'll be honest. I don't think that was the greatest paper in the world. So, yeah. So, what is the goal for today? I mean, that paper, I wanted to read some papers today, but also, you know, like I think there are very few recommender system courses, actually, that are good. Introduction, nearest neighbor collaborative, recommender system evaluation, capstone. Or maybe this is good, I don't know. You know, I think 4.4 is quite low, maybe. Course details. Best RecSys courses. The recommender system revolution. Okay. Okay, that was a really short one. That's it. Now keep reading. No? Okay. Uh, Just graduated, feeling low and having self-doubt. Uh, well, I mean, first, if you just graduated, uh, you probably have, okay, so like when you graduate, you have no job, right? And then you should apply for jobs, no? I mean, that's the everybody is unemployed when you just graduated. And I think having self doubt when you just graduated is normal, and everybody experiences that. I experienced that as well. You know, and there's a lot of people that experience imposter syndrome, where you don't feel that you are good enough, and I think that is a hard feeling to experience, but it is common, and I think try to be objective with the fact that you've been able to accomplish something that not many people do. You know, taking having just graduated, and then even though you have this self doubt, try to push towards what would improve the situation. So for you, I mean, that's searching for applying for jobs and continuing to while you are applying, continuing to improve. Did you make an announcement before you started stream? No. These streams are just chill, man. I don't put any pressure on like having many people watch them, or yeah, I don't this is just fun, you know. Yeah, I don't actually, yeah, it's just something I'm playing around with. Why are you focusing on recommender system? I'm really curious, and I think I would like to build projects and products with recommender systems. I think they have a really big impact. They generate a lot of revenue for machine learning in general. They are the most. They are the thing that revenue generate the most revenue, but have the least paper written. So I think it's just an interesting field, and there's a lot of opportunities in it. And I also, work a bit with recommender systems now. I'm 25, so yeah. I mean, like I think everybody is in learning phase all the time. Like you will never be out of an learning phase, and if you are, then you probably just just don't think that there is as it was in the past, where you would study for a couple of years and then you'd be completing your knowledge. That's just not the case. What kind of project would you like to build? I have some ideas, but I yeah, I don't know. We'll see. Maybe right now I just need to improve my skill in the topic, so I'll just make streams learning about it, and then maybe we'll build some projects and deploy them. That would be fun. But just like some fun dumb projects, like building a good like movie recommender system would be cool. That has all the movies, not just Netflix, sort of limited one, and try to play around with hey, what if we change the objective function? Could you build one when you aren't interested in when you aren't interested in profit that way? Could you build a better one? What was my question? I was going to ask something here. Okay, whatever. So, anyways, I'm curious, like, what the best. All right, let's check this out.
One of the highlights of the summer school, Xavier Amatrain here, and I hope I sort of kind of got his name
You got it,
approximately
man.
right. So if you were ever wondering why you see on Netflix what you see in terms of recommendations, he's the man. So he has a great team there, and well, my guess is that's one of the reasons why Netflix is so popular. So I'm really looking forward to his tutorials today and tomorrow. And yeah, take it away.
Thank you, Alex. Yeah, thank you for having me here, and it's a great pleasure. I would usually not give a lecture with a baseball cap, but you know, we just changed the Netflix logo, and this is the first swag that I got with the new logo. So I said, since I'm on camera, I'm going to be wearing it. And I also, the other thing I wouldn't do is to give a lecture with some kind of political statement like I have here, like Underwood 2016. Do people know who Frank Underwood is? Yeah, from House of Cards. Yes, I'm a big fan of House of Cards, one of the Netflix originals, so that's why I thought it would be good to do the lecture with this T-shirt. So I'm going to get started, and I'm going to be talking about recommender systems. I'll first maybe let me start by saying that I know there was another lecture by Deepak some days ago on a related topic. I'm happy to say that we coordinated well, and I know what he talked about, and I'm going to be complementing some of the things he talked about. I'm going to also be probably introducing some of the topics that he didn't mention. So that's all going to be, I think, interesting for all of you. And I am going to also be giving you a little bit of a practical examples from coming from Netflix and other companies. Whoops. Sorry. Let me make sure that I have my, I don't have power here, so it's going to be, no, I need to plug in the laptop somewhere that, do you know where that would be? Because otherwise it's going to be going into sleep mode all the time. Okay, so, yeah. So, first of all, I thought I would get started with a little bit about telling about who I am and how I got to be at Netflix and work on recommender system, which is kind of a long story. I've been doing research for almost 20 years now. But I'm originally from Barcelona, Spain. That's why my name, Xavier, is a little bit complicated to pronounce. And I did my PhD, interestingly, working on things related to signal processing and large-scale distributed software systems, particularly in the domain of audio and music. So I was in some research group that's called Music Technology Group, and I developed, among other things, a pretty popular open source framework that's called CLAMP for developing large-scale and real-time audio and music applications. So that was back then. And then I moved and I became research director at UCSB. At UCSB in Santa Barbara, I evolved a little bit and worked on, again, large-scale multimedia systems, but I was working on immersive virtual reality environments. I directed a project that's called the Allosphere, which is a huge immersive environment at UCSB. And then I went back to Barcelona after being in the US for a couple of years, and I went into a research lab for Telefónica. Telefónica is one of the largest phone companies and communication companies in the world. It's actually, I think, the third or the fourth. And I was doing research there. And there I really went back to something I had done during my PhD, which was machine learning, recommendation systems, information retrieval, and so on. So I was there for 4 or 5 years working on research related to these topics. And after that, I moved to Netflix, and I've been there for 3 years. So now I'm the director of something we call algorithms engineering team. And what we do there is basically develop all the algorithms that drive the personalization, the recommendation, also search. So all those algorithms are something that my team is working on. Okay, and here are some publications that I've worked on. I'm not going to do the kind of tutorial that I'm going to push a lot of my publications into the tutorial. I'll be talking about a couple of them, like tensor factorization, for example. But if you look me up in Google Scholar or anywhere, you'll see some of this.
Like, what a great resource from this guy. Like, this is actually I'm gonna use that a lot. This will be pretty interesting. I think this this might be actually really
You'll see
useful
some of
to get a yeah.
these publications, most of which the latest ones since say 2000 and something are related to machine learning recommendations and information retrieval. Okay, and some of the people that have contributed to this tutorial. So Justin is a manager in my team. He's at Netflix. Alexandros, he worked with me in Telefonica, and we've actually exchanged slides for similar tutorials that we've done at different schools. Bamshad at DePaul University, we're going to be giving a tutorial in KDD in New York about recommendations, and we've been preparing that tutorial, and part of these slides are going to go into it. And Francesco Ricci, a good friend, professor at University of Bolzano, very well known in the field. And Eric from Spotify, I basically put him out because I grabbed something that he recently published in a blog post, and I'm going to be talking about how they use deep learning for recommendations. I'm also going to be talking about how we use it for recommendations. Okay, so here is the outline of what I'm going to be talking about. And I have a lot of slides, a lot of topics to cover, and maybe if I get enough interaction, enough questions, which would be ideal, so I forgot to mention this, so please interrupt me, ask me questions. Maybe we won't be able to cover everything, but I've done it in such a way that I think the most important topics are going to be covered first. And if we don't get to, say, the practical example on Netflix, I've been talking about that many times in the past, and you can probably find videos in video lectures or YouTube where you're going to get a similar flavor of that. So it wouldn't bother me too much if we don't get there. So I really encourage you to ask questions during these 2 days. Okay? And before I get to even to the introduction, when you give a course like this, it's always a challenge to understand who you're going to have in the audience, right? Because they're going to be all over the place, people from undergrads to people that are doing research in the field, and then I'm trying to adapt the slides that I have in a way that the introduction is going to be very gentle, and then I try to get deeper into other topics as we advance in the course. But I'd like to have an initial sort of show of hands to give me some idea of who I have in the audience. So for example, how many of you are undergrads? No undergrads? PhD students? Okay, so the ones who raised your hand, PhD students in computer science. Okay, so most of them. How many of you are postdocs or researchers? Industry folks? Is there anybody from industry? Oh, yeah, okay. Okay, great. So I hope to meet many of you during the breaks or in some of the activities, but I get a sense of more or less who I have in the audience, which is good for me. Okay, so let me get started. And again, I know that Deepak talked about recommendations and about some of the algorithms. I saw his slides, and I think I felt that I could also give a different flavor of justification of why recommendation is important and what does it mean from both an academic but also an industry perspective. So I like to start with these 2 quotes that I think are pretty relevant. Chris Anderson, in a very popular book, The Long Tail, said something that struck me as interesting. He said that we are leaving the age of information and entering the age of recommendation, right? And he was saying that in the context of this information overload and how much information we have, and the idea that, yeah, having information is great, but unless you have a way to filter it out and to get to the important things, it's pretty much useless, right? And this other quote from CNN Money is very similar, right? Where it says, we're leaving the era of search and we're entering one of discovery, which is pretty much related to recommendation. So discovery is not when you're looking for something explicitly, when something that you didn't know it existed, it actually finds you. And I've been, for a long time, giving this idea of search versus recommendation, and the idea that basically, I mean, they're two sides of the same coin, and in search, the only difference is that you have an explicit query. In recommendation, that query is implicit and is basically made by the user and the context, right? Many methods are shared, many are specific to recommendation, but there's really a very thin line between, say, personalized search and recommendation. And again, the difference is that you don't have an explicit query. And when we talk about information overload, I've been using this quote from November 2006 for years, and it was saying that people read around 10 megabytes of material a day and hear 400 megabytes and see 1 megabyte of information a second. And I wanted to update it for the tutorial this time, and I looked it up, and I saw there was a study from this year from UCSD, and their prediction, which is almost, it's a very short time prediction, next year, right? 2015, the consumption, and that's per user, per person, is roughly 74 gigabytes of information a day, right? So when we're talking about the amount of information that is being consumed, not to mention the amount of information that is available and is not consumed. A very interesting book here by Barry Schwartz, The Paradox of Choice. He gives a lot of examples, a lot of experiments done on consumer preferences and consumer sciences of why having more choices, it's not always a good idea. So I think the most quoted example, and there's a video of Barry talking at Google precisely about this. It's one in where a shop, they had to sell some different flavors of jams, and they did an experiment. They put 6 different flavors, and they had so for people to come in and taste them, and they could taste them and buy them, of course. And then they did the same experiment, but instead of 6 flavors, they put 64 flavors. And the result of the experiment was, interestingly, that when there were only 6 flavors available, people bought much more than when they had 64. And what's the conclusion there? The conclusion is that people get overloaded when they see a lot of choices. And
So isn't this like exactly what Netflix does? Because every time I open the Netflix app, I get overwhelmed. There's so many things there.
making choices has a cost, and at the end of the day, people decide not to act just because they have too many choices to make, right? So we need to, if we want people to act, to make decisions, we need to narrow the choices and make their life easier. And that's what recommendations will do for you. Okay, so value of recommendations in Netflix, roughly 2/3 of the movies and TV shows that are watched are recommended. I think now we're up from that to roughly around 80% of the things that people watch come from some sort of recommendations. And even when people search, which is not, we don't consider it a recommendation, we do recommend things. I'll talk about that when I talk about the practical example of Netflix. In Google News, they published that when they introduced recommendations, they got 38% more click-through. Amazon, 35% of the sales come from recommendations. And ChoiceStream has a study where they found that if people had, if people would buy 28% more of the music if they really found what they were looking for. So all of this is about the sort of commercial and value that recommendations have for industry and for companies. And that's why, you know, it's a hot topic, and that's why you have 2 lectures in this course about recommendations, because it's something that it's based on machine learning algorithms. It's based on something that probably you guys are studying, but it's also very interesting and very relevant for companies and industry. Okay, so what is what we call the recommendation problem? And this is, has been cited and quoted many times. So the recommendation problem, we describe it as a utility function that is trying to estimate or predict how a user will like an item, right? And this is a very generic definition, and we'll get more into some instances of this definition. And what this prediction is going to be based on depends on what we have, right? It can be based on past behavior, and that will get us to collaborative filtering. It can be based on relation to other users, and we can talk about social recommendations, for example. It can be based on item similarity. We can do content-based recommendations based on that. It can be based on context and many different things, right? So depending on the kind of information that we have available, we'll address it as a different problem and use different methods. So more formally, if we have C be the set of all users and S be the set of all possible items that we can recommend, right? So basically our utility function U is going to be a function that measures the usefulness of some items S to the user C. And R, the subset of S that we will be recommending, is a totally ordered set.
The recommender problem. Let C be set of all users and S be set of all recommendables. Let U be a utility function measuring the usefulness of item S to user C, such that such that CXS gives you R, where R is a totally ordered set. All right, so you have a function that where you take those two sets, you get R, which is an ordered set where you have the best one for that user. And for each user C, we want to choose items S to maximize U, the usefulness. Utility is usually represented by rating, but can be any function.
And totally order is also an interesting concept that we will be getting to when we talk about learning to rank and how we use learning to rank approaches for recommendations. But the basic...
So one thing that I'm confused about is like if you, for the, we didn't look at that, but here, like the neural collaborative filtering paper, here, basically, it seems like their approach here is that you have embedding of the user and embedding of the item, and then you run that through some linear layers, and you get a score for that item and that user. So get basically like a rating from 1 to 5, and then you train it by using the actual target you had. So let's say that you have you have 5,000 movies or something in your, let's say, a very small data set there. And you basically run this for a particular user for all the movies, and you get a sorted order, right, of ranking. So you get like this movie is what you believe is the best, this is the second best, and so on. And you represent that to the user, maybe 5 of them or 10 of them or something. But it might be the case, right, that you want to have diversity, first of all, in your recommendation, so that maybe the top 5 are all very closely related. So you want to have some diversity. And then it might be the case also that, the ordering of how you present them has an impact on how they click on them. So ideally, it seems to me that you would like to have a neural network that also gives you in what order things should be shown. But that is not really taken into account in this one, right? I don't know exactly how. This is just for a single item, but you never just present a single item. So it just feels like it's a little bit incomplete. And there's something that I'm sort of missing when it comes to like how they do the final recommendation.
Basic idea.
So like this utility function,
is that we need to be able to order things, because at the end of the day, recommendation, just a search, is a way to order things in using some utility function.
I'll be right back.
In a way that you can prioritize some things versus others. And of course, for each user, we want to choose the subset of items in S that maximize this utility function. Okay, so any questions so far? No? So another way to look at, yes?
That's at one instant of time, the recommendation.
It is, yeah. It is at one instance of time. And I will be talking slightly about how time matters in this definition, but not too much. But I have a publication about the importance of time as a way to, how to incorporate the evolution of time into this kind of formulation. So another way to look at this, and actually this is a way to look at many of the sort of machine learning-based applications, is as a two-way process. We usually have two parts or two different processes that happen when we do the recommendations. We have an offline component, and the offline component may happen or not, depends on the model that you use. But basically, there is a learning process in which you may have users and items, and you're building some kind of model, some kind of clustering approach, for example. And then online, you have some context, and you have a decision process, and then you recommend the items, right? The trade-off between how much you do offline and how much you do online, depending on the method, that's something that, again, I won't get too much into it, but it's pretty relevant, especially on practical applications of deciding what method makes sense and how does it make sense. Depends a lot on how much you decide to do offline and what you need to do online, right? So for example, if you follow, let's say, any sort of map-reduce approach, you're going to be doing a lot of work here on the offline world. But however, incorporating context from a real-time application and context like the location or the time is going to be more difficult. Okay, so just a brief summary. We'll get into all of this, but just to get started, brief summary of recommendation approaches. So collaborative filtering, that's the one we're going to be spending most of the time on. So collaborative filtering is when we recommend things based only on past user behavior, right? So this approach is basically agnostic to what you're recommending. You don't need to have any domain expertise per se. So you don't need to know if you're recommending books, movies, music, or a car. And the idea is that you're going to be leveraging the relation between users. Some people get confused because there's two kinds of collaborative filtering approaches. We'll go into the user-based and item-based. Neither of them needs to have any information about the items, right? So the item-based approach, we will be making recommendations based on the similarity between items, but that similarity is going to be based only on past user behavior. So basically, we're going to be leveraging what users did in the past to infer a similarity function between items. On the other hand, content-based, that's the opposite. So here, we don't care about what the users did, and we based completely our approach on the domain knowledge, knowing what the items are, what they mean, and trying to find functions, usually similarity functions, that describe items as similar based on the content, so based on the description of the item. Personalized learning to rank, you will not, in sort of like traditional tutorials on recommendations or books, you won't see this as a first-class citizen in the recommendation approach. I've been saying for a couple of years already that learning to rank is an extremely important part of recommendation. So I try to bring this up early on when I talk about recommendations. And we'll talk about how to build personalized learning to rank. You can actually build learning to rank approaches that are both collaborative filtering or content-based. So I wouldn't call this as a completely different from the above, but I think it's important in itself enough to bring it up early on. Other things that we can do, demographics. So, and this is when you're doing things like advertising, which I didn't mention, it's kind of like one of the legs of sort of personalization. It's not, strictly speaking, I like to make it clear that it's very different to do targeted advertising from recommendation, but using demographic information is something that connects recommendations to targeted advertising. So basically, you're using data about the users, but data about where they come from, age group, and so on. Social recommendations, we'll talk about them. Here, you're leveraging the relation between users and whether they're connected and how strongly they are connected to infer whether they're going to like or they're going to buy something. And hybrids it's when you combine any or all of the above. And there is a section in my talk where we'll be talking about ways to hybridize recommendation approaches. Okay, questions? No? Okay, so yet another way to look at recommendation is to look at it as an instance of a data mining problem. This picture, which by the way, I now I see it doesn't look very well, comes from a chapter of a book. There's a book called Handbook on Recommendation Systems. I wrote a chapter for it which talks about data mining approaches to recommendations. And I was mentioning that basically the recommendation problem is just a different instance of a data mining problem where you have the data preparation step and you can do things like feature selection, dimensionality reduction, and so on. Then you have the data mining step per se, where you apply all the machine learning methods like clustering, classification, rule, association, rule mining, and so on. And then you have the post-processing, where you can do things like filtering, pattern interpretation, and so on. And this is a traditional sort of data mining problem. Now, that said, recommendation systems has a lot of other things that I won't be talking about here in this course, but are pretty important. And for example, the user interface, right? You can have the best algorithm in the world, but if the user interface is not accompanying and is not leveraging that algorithm, that approach is not going to be successful. And there are many examples of this. I've seen people trying to get value out of recommendations in a web page, but they're hiding the recommendations on the corner, on the right corner of the web page, and you need to scroll down to see them. So of course, it doesn't really matter how good your algorithm is if people are not going to see them. And then there are many things related to system requirement. How does it scale? How efficient it is? Privacy-related issues. Those are some of the things that I won't be getting into, but I just wanted them to bring that up. And serendipity, I'll get into a little bit, but it's something that is really not easy to address from a machine learning perspective, because this goes beyond the definition of the utility function that I was describing originally. Because serendipity, what it means, definition is when you find something that you didn't even know that you were looking for, right? So it's an unsought finding. So the idea in recommendations is that we need to optimize for what we know about the user and for maximizing that utility function. However, if we do it in a completely exploit way without introducing some sort of exploration, and I know Deepak spent quite some time talking about multi-arm bandits and explore exploit, right, where you're trying to find the right balance between both things. But the point is that in collaborative filtering, you can have some ways of introducing some controllable serendipity, but it's hard to, by itself, define what serendipity means, right? Because serendipity is something that, by its own definition, is something that it's not based on past data. It's going to be something that is completely an explore approach. Okay, so what works? And I like to start with this before I get into any of the methods, because if you had your startup and you only had that one developer and you had to choose one thing because you can't do everything, what would you do, right? So in the general case, what you would do is collaborative filtering, right? So that's the rule of thumb. It's if you don't tell me anything else about your problem and I have to choose for one, I would definitely go for collaborative filtering before any of the other approaches. Other approaches can be interesting if you have the right way to hybridize and combine it in different scenarios, and we'll talk about them. Things like cold starting when you don't have enough information, right? But in the general case, collaborative filtering is going to beat all the rest of the methods. And what matters in collaborative filtering? So data pre-processing is an important part of the problem and something that you need to be careful about it. You need to worry about things like denoising, removing global effects like user averages or item averages and so on. And a way to do that and to combine it even in a way that you can address the problem better is by doing dimensionality reduction. So things like matrix factorization, SVD, and so on. If I don't have any, again, if I didn't know anything about your problem, I had to go for try something, this is likely to work, I would say use matrix factorization and collaborative filtering. And if you have time, then go to the next step, which is, and then you can add another method, and you could combine it and add it, right? That would be sort of like my best guess. Okay, so let's start with getting a little bit more into the traditional methods, and we'll start with collaborative filtering. By the way, my categorization here between traditional and novel is not really meant to mean, strictly speaking, novel and traditional, but this is the classic ones that you would usually try first, and this is a little bit more advanced and introduce some novelties from latest research. Okay, so collaborative filtering, what are the ingredients we have? So we start with a list of users and items. And the only thing we have about the list of items is the opinion, or whether some users liked or did something with those items or not. The kind of data that we usually will work with can be of two kinds, explicit or implicit. So an explicit is when we do have a rating or something that the user was explicitly giving us a feedback on that item, knowing that it was giving a feedback on that item. Sometimes the rating of that information that we have is implicit, and I would say not only sometimes, most of the time it's going to be implicit. And that implicit information is actually much more readily available and easy to get. And I will talk about it at the end of the course when I talk about Netflix as an example of recommendations. But again, if I had to choose between explicit and implicit, and this is going to sound weird because some of you, if you remember the Netflix prize, and I'll talk about it, it was based around ratings, which is explicit opinion. I would say you're usually much better off going with implicit than explicit. And there are many reasons for that, but basically implicit information is easier to get. You don't need to get the user involved in the act of recommendation. And second of all is, although it might seem counterintuitive, explicit information like ratings, it's pretty noisy. So just to give you an example, when people rate the kinds of movies that they like, they tend to give, most of the people tend, including myself, we tend to give an aspirational rating. So basically we give a rating really to the quality of the movie and what we would really like to watch. Like if we watch a documentary that is really good and won an Oscar, we'll give it 5 stars because like, oh, that's a really good documentary. Does that mean that we want to watch that documentary every night? Probably not, right? We're going to be watching comedies that are not so good, but they're a good laugh after a hard day at school or work. And those are the things that we like, but we're only going to be giving that movie 2 or 3 stars, right? So then there's a sort of like a contradiction between some of the explicit preference information that we'll get from the users and what the users really want to get. So, and that's the same thing for things like shopping and so on, right? So explicit information, it's a little bit tricky to deal with, and it's much harder to get. That's the other thing. If you want to get big data, with implicit information, you'll get it. With explicit, it's much harder. Okay, so we're going to have some sort of data or information about the relation between a user and an item. Then we're going to have an active user, that person in the room whom we're recommending for. And then we're going to have a metric for measuring similarity between users and a method for selecting a subset of neighbors. And finally, a method for predicting a rating. So this is pretty easy, right? So if I choose somebody in the room and I say, I'm going to recommend something for you, I'm going to be looking around the room and say, okay, let me find the 5 people that are more similar to you, and I'll pick 5 here. Say, I'll ask those 5 people, like, hey, what do you like? I'll kind of combine that in some sort of average or some way, and then I'll go to him and say, hey, I've talked to these 5 people, and I think that you would really like this. Basically, that's the idea, right? And when I talk to those people, I don't ask them any information about the items themselves. I just ask them about what do you like, right? And that's the basic idea of collaborative filtering. There is no domain knowledge. I don't care. The same exact method could be used for music, movies, books, and I wouldn't change anything about my question. The only thing I would change is I would go to those people and ask them, what's your favorite movie? What's your favorite TV show? What's your favorite song? What's your favorite book? And I would average that and go back and recommend that. So more formally, we identify a set of ratings for the target user. We identify the users that are most similar to the target user according to a similarity function. Then we identify the products these similar users liked. And then we generate a prediction, a rating for each one of these products. And based on this predicted rating, we sort the items and we recommend the top n. Right? So this is the basic approach to collaborative filtering. And all the other things that I will throw in later on, including things like learning to rank and deep learning and so on, have flavor of exactly this same thing. So what's the pro of collaborative filtering? So it requires minimal knowledge, in particular minimal domain knowledge. Right? We don't need to know anything about the items. We can apply exactly the same method independently of what we're recommending. We don't have to have any internal or structural definition for the items or any even information about the items. And in most cases, produces good enough recommendations. As I said, this would be my preferred method if I didn't know anything else about your problem. Even if I knew about your problem, I would probably end up saying collaborative filtering is a good approach. Now, the cons is that you need data, right? That's a tricky thing. Going back to the example of, oh, I have a startup and I need to figure out a method to get started with to do recommendations. If I think about what I said before, like, oh, go with collaborative filtering, that's easy to say, but to do collaborative filtering, I need people and I need data from those people, right? So that's the tricky part of collaborative filtering. Unless I have users and I have data from those users, I'm not going to be able to bootstrap the system, and I'm not going to be able to give good quality recommendations. The other thing, and these are more minor in some sense, is that I need to have sort of like a standardized way to refer to the products or the items. And this is related to another issue I'll mention later, which is sparsity. If your catalog of items is really, really large, think Amazon, for example, or eBay with millions of products, right? Unless users buy the exact same item over and over again, it's a tricky thing. Then you need to start getting smarter about what you do, because in eBay, maybe not two people buy the exact same thing, right? They buy things that are similar, so then you need to figure out what the similarity is, and that's more tricky. In the case of Netflix, for example, do I need the microphone?
Well,
what do you think?
I guess people in the last row will be able to hear you a bit.
Okay, that guy is sleeping
Well,
in
they
the...
might at least wake up.
I think I'm going to wake up that guy in the last row now. Okay. So, sorry, I was talking about the fact that if we have a large catalog of items, you need to be able to identify things that were bought were exactly the same. We're also assuming that prior behavior determined current behavior, so that's something that you need to address. If you want to add any information about context, you need to add it in a very different way. So what's the difference between personalized and non-personalized? So I'll get to some numbers now, but the idea is, if I don't have anything better to do, it's always a good idea to recommend the most popular stuff, right? So unless you're sure that you can do better than the most popular, just get started with the most popular stuff, right? Because that's going to be your baseline. And I've seen many, many times, including papers and publications and practical approaches, where people were doing approaches in which they were not comparing it at least against the pure baseline of popularity. And if you're building a personalized approach and you're not doing better than popularity, there's something wrong, right? So the basic idea is, if I didn't, again, going to the example of I'm trying to do collaborative filtering for him and finding a good movie to recommend to him, and I had to find the 5 most similar people in the room to do that recommendation, right? That step in itself is a little bit tricky, right? Because I don't know him, so it's like, how can I find the 5 most similar people in the room? So if I don't know enough, the best thing I can do is just, I'll just ask everybody. I'll just ask everybody about their favorite movie. I'll do an average, and I'll go to him and say, hey, chances are you're going to like this movie, because most people in the room like it, right? And I don't know who's most similar to you. So that should be my baseline, and that's a first approach. And if we put that into numbers, and here, what I'm putting here is the mean average error of some typical data sets. By the way, these are, besides the Netflix data set, which is not publicly available, unfortunately, anymore, Gesture, Movie Lens, and Each Movies are publicly available data sets that are used for recommendations. So I think this is an interesting comparison, which is, what's the difference between the non-personalized mean average error? So this is basically the popularity, the most popular thing, and the personalized, right? And you see that there is a difference. So yes, if we do some personalization, and this is, by the way, this is the easier collaborative filtering nearest neighbor approach that we'll talk about. So you can do better than this. But the idea is, by doing personalized, you can do better, of course, than by using the global popularity. But you can do just a little bit better. It's not easy to beat popularity. And this is actually highlighted in this other plot that I have. And this is related to the Netflix price, where here, by the way, this is the root mean square error. So comparable, different than the mean average error, but the idea is the same. So I think this is a very interesting plot to sort of like internalize if you're working or if you're thinking about recommendations, which is the idea that if you use, what's the root mean square error of a completely random recommendation? This is a 5-point Likert scale, so this is 1 to 5 ratings. So if you're completely random, you'll be here. If you use the average, you're going to be right over here. So that's roughly, I think it's 1 point, it's not even 1.1, so it's 1.05, right? So this is the root mean square error. So basically, you're going to be making an error which is slightly over 1 star over the 5 stars, right? So if I predict a 4 for you, it might be a 3, or it might be a 5, but not more. And this is, so this is the Cinematch. This is the original approach that was put out for the Netflix prize, and we told people if you bid this, you'll get $1 million. Look how close it is to the average, right? And the price, which took almost 4 years and a lot of people thinking about and a lot of CPU cycles, was 0.81, a little bit under 0.81, right? So the point here is that it's fairly easy to come up with reasonable recommendations, and the reasonable recommendations can almost be the average ones. And it's pretty hard to get down to be much better than the popularity. However, of course, and the reason that I'm here talking to you, and the reason we gave $1 million for this here, is because this slight difference a slight difference in the numbers can make a huge difference in the product, right? So every time, and this is old news, right? This was 2006 or 2009, sorry. But if I think nowadays, every single A/B test we do at Netflix where we improve this just slightly and we put it a little bit below has a value of thousands, if not millions of dollars, right? So, but in numbers, if you compare it, it's hard. And if you can do with any domain, when you compare the non-personalized versus the personalized, it's hard to beat that thing. Now, when you think about any method that you work on, it's also giving you a good intuition. It's like, well, I'll fit the average into my method, and then all I need to do is have my method improve that average in some way, right? And one way is, as we were saying before, I start with all the neighbors, and then I reduce it to a subset. If I'm able to just remove a few of the bad neighbors, that's going to improve my results, right? Question? Now, when you think about any method that you work on, it's also giving you a good intuition. It's like, well, I'll fit the average into my method, and then all I need to do is have my method improve that average in some way, right? And one way is, as we were saying before, I start with all the neighbors, and then I reduce it to a subset. If I'm able to just remove a few of the bad neighbors, that's going to improve my results, right? Question?
You consistently get improvements, and so whenever you get an improvement in the mean error, you consistently get improvements in revenue?
That's a good question, and it's not as easy as that. And the reason it's not as easy is because it's the mapping between the offline metrics that you optimize in the lab, right? My team is optimizing a number of offline metrics whenever they're doing the machine learning improvements, don't directly correlate with what you see from the users online. So it's a little bit more involved and more tricky. There's not a linear relation. You actually need to build your own regression models from the offline metrics to the online. But directionally, it is true, right? So any improvement you do directionally will show improvement. The question is about how much you need to improve in order to get that delta that makes a difference. Yes?
You recommended collaborative filtering for like starting up as a first step. But doesn't it depend a lot on what features you are looking at? Like you could get, I guess, huge difference if you're choosing the right features in collaborative filtering rather than some other features.
Well, the point I was trying to make is that in collaborative filtering, you don't really need features, although that was an overstatement if I think about it. So there is, my overall point is like I'm treating user feedback overall as a feature, and I'm assuming that you don't need to do any more feature engineering than just take the feedback, the ratings as they are, or the clicks, right? So in that sense, my recommendation was independent of the feature because I wasn't even thinking about converting clicks into features. They're just clicks, right? And you can't do much to clicks, although that's not entirely true, right? But I'm not even going to the realm of feature engineering. I'm just thinking about pure click feedback and how to feed that into collaborative filtering. In other approaches, the feature engineering step is much more important because then you do need, if you're doing a content-based approach, there is no way out of the feature engineering step, right? You need to turn a movie into a set of features because otherwise you can't recommend it. In collaborative filtering, you can avoid the feature engineering step by basically saying, well, I just have a matrix of user items and clicks, and I work with that. I don't need the feature engineering step, although you can still do it, right? Okay. So user-based collaborative filtering, we have our similar people, we have a weighted sum, we have the target user, and we recommend. So if we turn that into a little more formal, what does it mean? So basically, we have a collection of users, and that's going to be indexed by I, collection of products on J, and the dimensions here are N and M. So that determines an N times M matrix of ratings. And when I say ratings, again, ratings or clicks, it doesn't matter. We're going to have a number there, or we're just going to have a binary 0, 1. And we're going to have a question mark, and that question mark will get to what does it mean, because that's basically the unknown that we don't know in the matrix if the user did not rate the product or did not buy the product, right? So basically, again, going back to the previous slide, weighted sum of the neighbors.
Okay, so what is he saying here? Basically that like building a simple, reasonable recommender system is easy, but to make it good requires a lot of work. So here he is talking about, like some similarity by Pearson correlation, or a cosine similarity measure maybe. But I just wanted to check here first of all, like let's want to build something at the same time a little bit. So just want to see. So does this work even? So movies and ratings, and how do you merge them? That's a lot of things to merge. Okay, so if we check now, okay, we have movie ID. Okay, so data.shape, all right, became 2 million. Yeah, okay, so we have, in the beginning, we had this, just a movie. Now we have a bunch of duplicated rows for each user, and then the rating, and then also the timestamp. And then the idea is create a user movie matrix with ratings as values. Why? Fill no number with 0, split the data, calculate the cosine between users. Oh, well, that's super simple, right? So we just do what exactly? We just training data users and then predict. That is actually super simple. No, that's like just taking the,
The prediction for the user is just going to be a combination or a weight of every user and the rating that the user gave to that item. Or we can do something a little bit more fancy, if you will, which is basically using this is going to be the rating average, and measure what's the delta of each of the neighbors compared to the average of the item rating, and do, again, a weighted combination of that delta between the average and the and each of the users' rating. So the idea here is I either take all the users that are in my neighborhood and I weight their rating and I predict my rating as such, or, and that's what's usually recommended, or I remove the item average first, and then I combine the deltas from that from that item average to that item, or we can do something a little bit more fancy, if you will, which is basically using this is going to be the rating average, and measure what's the delta of each of the neighbors compared to the average of the item rating, and do again a weighted combination of that delta between the average and the and each of the users' rating. So the idea here is I either take all the users that are in my neighborhood and I weight their rating and I predict my rating as such, or, and that's what's usually recommended, or I remove the item average first, and then I combine the deltas from that from that item average of my neighbors in order to determine, what is going to be my rating. Okay? Now, the only thing that's missing here is what's this weight going to be? How do I weight each of the neighbors? And each of the weights for the neighbors is going to be based on this idea of similarity. So when I found the 5 people that were more similar to him, instead of just thinking, well, they're all equally similar, and I'm just going to weight equally whatever they said, what I'm going to do is say, well, the most similar person is going to get more vote than the least similar person, right? So basically, we need to have a similarity function which can be computed as a Pearson correlation or a cosine similarity. And that similarity function, we can use it for 2 things. First of all, it's going to be used to determine the neighbors. So basically, this boundary, if I'm using, say, I'm going to use the 10 best neighbors. The 10 best neighbors are going to be determined by the similarity function, first thing. Second, once I have the neighbors, given that I have the similarity function, now I can use that to weight each of the opinions of the users and plug it in here and use it as a weighted average for the ratings of that neighbor to produce the prediction for the rating of the target user. Okay? Yes?
You have ratings and clicks. How do you combine both kind of?
Hold that question because we'll get there. For now, we have either ratings or clicks, but you can combine that in different ways. And the question is a little bit more advanced than what I'm talking about right now, but we'll get to that question soon. Another question?
Isn't it better to use all the users and the space because for some items you wouldn't have anything from the users or similar to you?
That's a good question. So the question is, why do we restrict the number of users? Because the problem, if we restrict the number of users, then chances that those users have rated all the items become less, right? And when we talk about dimensionality reduction and matrix factorization, we actually hit on precisely that point. One of the problems with this method is data sparsity, and you're going to have problems if the neighborhood or the users in the neighborhood have not rated the items that you're trying to predict. And of course, if your dimensionality of your item space is large, that's going to happen very often. And you're going to have a large neighborhood, and that's not computationally very efficient. So we're now basically hitting all the limitations of this method. This is a method that is easy to understand and easy to explain, and it's not bad, but it has a bunch of limitations, and some of them are becoming apparent just by thinking about it like, well, is this really going to work? It's easy to make it work in the context of a few users and a few items, right? But if you try to scale it, you realize there are some issues. Yeah.
What are the practical limits on how sparse the matrix could be?
For the nearest neighbor method to work, I mean, the definition of work is a little bit tricky, right? What does work mean? If it means being better than the global popularity, it can be pretty sparse. I mean, you can have a sparsity of less than 0.1%, and still work in the sense that you're going to get better than the global popularity. And of course, it all depends on how you trade off your sparsity against with the number of neighbors you use, and the computational complexity. That's the other problem, right? Like how costly it's going to be. Do you have all the time in the world? And like, I don't care if it takes 3 days to compute, right? But if you start trading off all those things and say, well, I want it to be more efficient, to work faster, to not have to compute so many neighbors and so on, then it gets tricky to make it practical. Right? Okay, so just to give you an example here, and I think this is clear enough, so I'll just quickly move over. So so this guy over here is my target user. So I find another user that seems to be similar because she's rated the similar movies, right, or TV shows, and I'm computing here the Pearson correlation and say, oh, these users are 0.87. By the way, these users, when I say it's not available, is because what's happening here is they don't have any overlapping ratings, so I can't compute the similarity. Okay, so 0.87. This guy's similarity is 1. When you look at the Pearson correlation formula, you'll realize that if the users have rated only one single item and their rating is either both over the average or under the average, the similarity will be 1. If they're over and under, it will be -1. Right? So that's a property of the Pearson correlation. So in this case, they're both over the average, so it's 1. And in this case, 1 is over the average, 1 is under the average, it's -1. So I have these 3 neighbors, 0.87, 1, and -1 is the similarity to the target user. I combine and I compute the weighted average of the ratings for these 3 users, and I get the prediction for all the ratings. So I basically filled in this row for this user, giving the information that I had for all the other users. Okay? And I'm not saying, of course, I'm not saying this is a great prediction. It's based on very few neighbors and very few ratings. Right? But we have a way of doing something that chances are it's going to be better than if we just took the item average. Okay. Okay, so challenges, I think we've already touched upon several of those. So challenges of nearest neighbor collaborative filtering is, first of all, overall sparsity, right? If we have sparsity under 1%, in many cases, this is going to be challenged to fill in that matrix and to find those neighborhoods and to do that in a way that makes sense. The scalability is another one we talked about. Nearest neighbors requires computation that grows with the number of users and the number of items. And there can be a poor relationship among like-minded but sparse rating users, right? There's this thing about if I only have one rating in common, it turns out that I get a similarity of 1 just because I happen to have rated that one single movie the same, not even the same, if I happen to have rated above average or below average. So the solution for all these things is the use of latent models, and we'll get to them in a bit. And latent models or matrix factorization, SVD, and so on, is going to be a way of compacting that matrix into a fully dense matrix where we can apply similar concepts, but then in a much more fundamental way. And I know you've already talked about matrix factorization with Deepak, so just to hit on this maybe a little bit more, the basic idea for this is if instead of my matrix representing items, which is going to be a very sparse space, I was able to recommend topics, for example, and it doesn't necessarily need to be topics, but it can be dimensions in my space, like horror or dark movies or comedies or movies that make me cry, right? I could compact that space into something that made sense and it was much smaller and much denser populated, right? So that's the idea of latent models. Okay, so item-based collaborative filtering, I'm going to go quickly over this because it's basically the same, but instead of users, now we're going to do items, right? So I'm going to find similar items, and I'm going to be inferring that if you really like this item, you're going to really be liking items that are similar to that one, right? And again, the key thing to remember, we don't know anything about the items, so we don't know what they are. We don't even know their name or their title. We're going to be basing our similarity function, again, on what users did, right? So we're going to be defining that two items are similar if the same users like those items, right? So if same subset of users like two different kinds of items, we'll consider that those items are similar. And we only use, again, past ratings or interaction from the users. So we can use the cosine similarity and correlation-based similarities or adjusted cosine similarities. I'm just going to go over this quickly. And we can predict the rating for an item also using a weighted average of the items that are similar. And
So I guess like what he's talking about here is very similar to what we're doing here. We're just taking, actually, let's just take a look at this. I don't know why one would want to do this. Okay. Yeah, I don't think this is the best idea here. I mean, what are we doing? We are first merging them. So for the prediction, we're taking the mean user rating. Yeah, I mean, I wonder also like how do you do this for very large matrices? Just the underlying idea makes sense, right? If you just do this for all, then you just check which are the closest items, basically, and then I guess you would look at what the user has rated those closest item and take an average of those.
if we go to the same example that we had before, but now we try to do item-based collaborative filtering. So what I'm trying to do here, my target item is this one, The Walking Dead. So now, instead of having a target user, I have a target item, right? So I'll look for, I'm trying to find the similarity between this item and this item, okay? And I find in this case is -1. In this case, the similarity between this item and this item is also -1. The similarity between this item and this item is 0.86. This item and this item is 1. This one, it cannot be computed because I don't have two users that have rated both Walking Dead and Breaking Bad. And the last one is then the combined weighted average of the ratings that I have and the similarities between the items and themselves, right? So the basic idea is I'm just filling the matrix, but in the other direction. And instead of using the similarity between the users, I'm using the similarity between the items. And to compute the similarity between the items, I can use correlation-based similarities cosines or weighted cosine similarities. But I'm using the exact same information that I was using before to do the filling the matrix in one direction or the other. Okay, so I'm looking at the time and I want to move on, but I'll just do a quick recap of the neighborhood-based collaborative filtering. So we usually have large product sets and the user ratings or user interaction just for a small percentage. And here you have an example in the case of Amazon and their catalog of millions of books, right? So the probability that two users have bought 100, the two users that have bought 100 books have a common book is 0.01, right? And with 50 and 10, it's going to be 0.00002. So it's going to be really hard to find those two users that have bought or rated comparable things to even form a neighborhood. That's a real challenge. And to the question of, you were asking, like, you know, a rule of thumb of like how many, what's the density of the matrix in order to make sense. So more or less, if you have a number of users comparable to 1/10 of the size of your catalog, you can probably get started. But that's assuming, you know, an interaction model which is similar to the one that I'm saying here. So in the case, going a little bit more into this problem of the sparsity issue, if we take the Netflix data set for the Netflix prize, by the way, is everyone familiar with the Netflix prize and the $1 million Netflix prize? Because I'll describe it a little bit more later, but who is not familiar with the Netflix prize? Okay, so just a couple of people, but just 1 minute description. So this was a prize that started in 2006. Netflix put out a data set. It was made of 500,000 users and 17,000 movies, and some ratings, actually only 100 million ratings.
We're loading the movies, we're creating movies, dictionary, movies.title.values, index, create a dictionary to map movie ID to title, map movie titles to the ratings, create a sparse matrix. Okay, let's just say that we do this first. Yeah, we should probably just start with a subset of that data because I don't know, like this is really large. Okay, well, he was able to do it, so I'm not sure why I'm not able to.
Sorry. 100,000 of ratings to this 500,000 users and 17,000 movies. And the goal of the prize was to be able to beat the Cinematch model, which I
think we're gonna get that it crashes. Probably it's some limitation on my computer, maybe. Like it only has 8 gigabytes of RAM, so I mean, probably I should do this on. All right, so let's just copy this link. Mm-hmm. I think it's a good idea to, like, while we are listening to this, just try and implement some
I talked
stuff.
about before, which was a very simple, actually nearest neighbor based approach. And given that data set, there were a number of teams over 3 years that were trying to beat 10% of the original method. And the way that this was being measured was using the root mean square error. So basically, over 3 years, there were a bunch of teams trying to beat that. And what I'm trying to illustrate here is the sparsity of the data set. So basically, if you take 500,000 times 17,000, you get 8,500 million positions in the matrix, and you have that most of those positions in that matrix are going to be zeros, right? You have very few known zeros in that matrix. And then doing standard collaborative filtering based nearest neighbor collaborative filtering is going to be very challenging. That's why dimensionality reduction techniques are going to be much more powerful. Okay, the scalability, I already talked about this. It's really hard, well, not hard, it's costly to compute the similarity between all the users or all the items in your data set.
All right. I mean, I let's see. I will take a break, I think. I will I mean I really think this is probably one of the best resources I've come across so far. And that his lecture here, I'm definitely gonna watch them. Like watch these 2 lectures and then just try to go through this and try to start implementing stuff, just starting with basics. I think the movie lens dataset is a really good starting point because you have everything here. So we'll do that in the upcoming streams. Yeah, I mean, like these streams are hacky. They're like I mean, they're not polished or anything, right? But I thought, hey, it could be a chill way to also document some stuff of what I'm doing. And I'm working on, like, my goal is to start creating a recommender system playlist with from scratch implementations and so on. So that will be upcoming in the future. And yeah. But yeah, I'll probably, I mean, I don't have a, like, as you can see, like, I don't have a structure for these streams or anything. And yeah, it's just like, I hope that people can come by, ask questions, and just have a chat. And then maybe some streams are interesting of like, we're going to implement something, or, you know, we'll see exactly how it will go. But yeah, I think I'll stop the stream for now. I'm gonna check these out and then go through this one. Maybe I was hoping to find like a good course as well. I've taken some, but I haven't found like a really great course on specifically recommender systems, unfortunately. But maybe in the future. All right, I don't know if there's anyone still here, but anyways. Thanks for joining the stream so far, and see you in the next one.